For part one, we're going to talk about the sampling distribution for proportion. Now, recall this difference between population parameters and sample statistics. So the mean of the population, it's referred to as mu, this Greek letter mu, while the mean of a sample we denote with x bar, an x with a line over it. In general, recall that we typically use Greek letters to refer to population parameters, and typically we use Latin or Roman letters to refer to sample statistics. For proportion, there's a slight difference. You will usually see p refer to a proportion in the population, while p hat, a p with a little caret over it, will refer to a proportion from a sample. However, sometimes you may see pi, the Greek letter pi, for a population proportion, and pi hat for a sample proportion. Just to be clear here, this is one slight deviation from this general rule that we have Greek letters for population parameters and Latin or Roman letters for sample statistics. The other key point here is that sometimes you will see p refer to the probability or p-value of a test statistic, while pi is a mathematical constant. So be careful, try to read the context about whether some symbol is referring to a population parameter, a sample statistic, or some other quantity that we're looking at, such as a mathematical constant or a p-value. For this lecture, we will try to hew to the convention of using p to refer to the population proportion and p hat to refer to the proportion from a sample. Now, the thing about a proportion is that we can think of a proportion as a mean. Right? So, for example, suppose we have a binary categorical variable on banning smoking in public spaces. And suppose this variable is coded as approve or disapprove. If we code approve as 1, so everyone who says that they approve gets a 1 in their cell in the data frame, and disapprove we code as 0, and then we calculate the mean based on that value of 1 and 0 for all respondents, then we will obtain the proportion of respondents who approve of the smoking ban. In this sort of convention, or this sort of terminology, the value of 1 we typically refer to as a success, and we typically call 0 a failure. Now, these are in quotes because it may not actually be a real-world failure. You might call or code something as a failure, but in your view, it might actually be a success. So just to be clear, by convention, 1 is a success, 0 is a failure. But in real life, right, a success could be something that is bad, maybe getting sick. You might code as 1, but when you hear people talk about a success or failure condition, or successes and failures in the context of coding a binary categorical variable as 1s and 0s, keep in mind that that's what they're talking about. They're talking about that 1 is referred to as a success and 0 is referred to as a failure. Now, we can think of the proportion as a mean. So suppose we have a random sample and we have these 3 sets, or rather 4 sets of values. So one person gets a value of 1, the next person gets a value of 0, the third person gets a value of 1, and the fourth person gets a value of 1. So in this sort of context, person 1 might approve, person 2 disapproves, and people 3 and 4, they both approve. Now, coding this set of responses into 1s and 0s, we can calculate a mean, all right? And that mean of that sample is just the sample proportion. So we get 1 plus 0 plus 1 plus 1 divided by 4, we get 0.75, right? That's the proportion of people who approve of this smoking ban. So, and that just refers to the fact that 3 out of these 4 people have 1s, right? So the thing about treating a sample proportion as a sample mean, the key point is the sampling distribution for p hat, for the sample proportion, it will be approximately normal as long as the success-failure condition holds. Now, what is the success-failure condition? Assuming that we calculate p hat, the sample proportion, from a random sample, the sampling distribution of p hat is approximately normal as long as we expect to see at least 10 successes and 10 failures in our sample, where success and failures defined as before. Successes are those with 1s, and failures are those with 0s. Now, we can write this out as long as n times p, where n is a sample size, p is the population proportion, as long as n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then this condition holds. Then we can say that we can treat the sample proportion as a sample mean, and the sampling distribution of that sample proportion is approximately normal. Now, the key point here is that we do not actually observe P. Right? If we did, we would have a census. We wouldn't have to do any inferences. P is the proportion in the population. Right? We know the sample size, lowercase n, but we do not know the population proportion P unless we conduct a census. So the key point here is that we have to assume the success failure condition holds, but we can use our sample proportion P hat to assess how confident we are or the validity of this particular assumption. So we can examine this success failure condition using our sample proportion. So in the previous example, we have this small sample of 4 people. 3 people approve, 1 person disapproves, so we have 3 ones, and we have a single person with a value of 0. And we calculated P hat, the sample proportion, as 0.75. Now we can test the success failure condition using our sample proportion. Right? We never fully know if we know we're actually violating the success failure condition, but we can gain some confidence. If our sample proportion, as a point estimate for the population proportion, leads to this violation of the success failure condition, we probably shouldn't treat that sample proportion as being approximately normally distributed. So let's plug in P hat for P. Then we get these 2 values for the successes and failures. The expected successes are n times P, which is 3, right? In this case, 4 times 0.75. So we expect about 3 successes. In terms of the expected failures, we have n times 1 minus P, or 4 times 0.25, which is 1. So we have about 1 expected failure. Both of these are less than 10. Right? 3 is less than 10, and 1 is less than 10. So in this particular example, the success failure condition does not hold up. So we wouldn't really expect the sampling distribution of P hat to be normally distributed, and so we really couldn't treat it as a sample mean using the standard normal distribution. So let's go through an example and really kind of check out this idea. So let's look at the census of Turin, Italy. One of the variables is whether or not a respondent is the head of the household. So they went around, they asked everybody in these homes in Turin, Italy, are you the head of the household or not? And people said yes or no. So let's code yes as 1 and no as 0. So in this example, we're going to say a success is 1, you're the head of the household. A failure is no, it's 0, you're not the head of the household. This is what our data set looks like. Now the key point here is that this is a census. So we have the entire population of Turin, Italy in 1705. So this is the original binary categorical variable. Right? People are coded as yes or no, are you the head of the household or not? And we're showing here the first 10 rows. What we can do is we can recode this variable in terms of 1s and 0s. Right? That's all we've done here. We've changed this categorical variable into a discrete numerical variable where every person who gets a value of yes now is coded as 1, and everyone who has a value of no now gets a value of 0. So let's calculate the proportion in the population. Just conducting our basic summary of this data set for this particular variable, we find that the proportion in the population is about 1/3. It's about 0.33. That means about 33% of the people in Turin, Italy are heads of households, which might suggest pretty small households. So the thing about this is that that's the population proportion. Typically, we wouldn't know that, but in this case, we can actually examine what happens to the success failure condition for different sample sizes. So suppose we had a sample size of 3 randomly collected from the entire population of Turin, Italy during this time period, and we calculated a sample proportion. Well, we can test the success failure condition actually using P, because we have P, we have that population proportion. So if the sample size is 3, then we would expect there to be about 1 success, right? And we'd expect there to be about 3 failures, right? So with a sample size of 3, the success failure conditions, they don't hold because both of those are less than 10. The expected number of successes and the expected number of failures are both less than 10. So with a sample size of 3, we wouldn't be very confident that the sampling distribution of P hat would be normal. We wouldn't expect it to be. Right? So let's see what would happen if we had a sample size of 30 and we calculated a sample proportion from this population. So let's test the success-failure condition. The expected number of successes is 30 times 0.33. Right? That's about 9.99. And then the expected number of failures is about 20. 30 times 0.67. So in this case, all right, we'd say, well, sample size of 30 is pretty darn close. It's pretty close. So we'd say that the sampling distribution would be approximately normal. All right, we might want a little bit larger of a sample size, but it's going to be approximately normal since both of these are 9.99 rounded up is very close to 10. Right, now let's see what happens if we have a sample size of 50. Right? The idea is we're testing the success-failure condition. We're seeing what are the expected number of successes or failures for given sample sizes. Because in this case, we know the population proportion, so we can actually examine these assumptions. Typically, we would use p hat instead of p. So let's look at a sample size of 50. N times p, right, is about 16.55. So in a sample size about 50, we'd expect about 16.55 successes and about 33.5 failures. Right? Out of that sample of 50, we'd expect 16.55 to be heads of households and 33.5 people to be not heads of households. So in this case, yeah, both of those values are greater than 10. The expected number of successes and the expected number of failures are both greater than 10. So we would expect p hat, the sample proportion, to be approximately normal for this particular sample size and for this particular population proportion. So let's examine these distributions. Right? We can create these sampling distributions of p hat since we know the population proportion. Again, these are sampling distributions. I've overlaid these sampling distributions with a normal curve so we can kind of compare. So in this example, we have taken 1,000 different samples of size 3, and each time we take a random sample from this population, we calculate the sample proportion, the p hat. And then we create this distribution. That's represented by the histogram. Now you can see with a sample size of 3, right, we really only have 4 particular values, right, just because of the way of the fact that each person is only coded 1 and 0, and our sample size is 3, we don't have that much variation in terms of the number of possible values of p hat. And you can see that we've overlaid the normal curve, the standard normal curve over this, and you can see that it's not really normal, right, with a sample size this small. That reflects the fact that the expected number of successes and the expected number of failures, right, that success-failure condition is violated with a sample size of 3 and this particular population proportion of 0.33. Let's see what happens when we have a sample size of 5. We can see that that sampling distribution of p hat is a little bit more normal. Right? There's still gaps because of the number of possible values of p hat is rather limited, but it looks a little bit more normal. You can see that just comparing it to that normal curve, that sampling distribution of p hat looks a little bit more normal. But again, the success-failure condition still does not hold, if you recall, with a sample size of 5. Let's see if sample size of 15. Right? You can see that distribution of p hat's looking a little bit more normal. Now we have a sample size of 30. All right, this is approximately normal. If you recall, with a sample size of 30, we were pretty close to actually meeting the assumptions of the success-failure condition. Right? The number expected of successes is about 10. The number of expected failures is about 20. So both of those are greater than or equal to 10, roughly. And so with the sample size of 30, you can see this. Right? The sampling distribution of p hat in this case, as denoted by the histogram, it's approximately normal. Right? It's not quite, but it's pretty close. All right. If we look at a sample size of 50, it's really quite close to normal. And a sample size of 1,000, it's really very close to normal. So you can see that with that larger sample size, right, that sampling distribution for that sample proportion can be approximated by a normal distribution. And with that, we're going to look through a few examples of exploring this idea of the success-failure condition.